In the last couple of videos, what we looked at were some features of NMR spectra, specifically focusing on the chemical shift, the location along the x-axis, where we see a particular signal for a proton or a carbon atom in an NMR spectrum. We learned that that can give us some information about what types of functional groups are present in a molecule, because the chemical shift is dependent upon the so-called chemical environment of a particular proton. That chemical environment is driven by what types of atoms are nearby, particularly whether those atoms and groups are electron donating or electron withdrawing. Now, in this video, we are going to take things a step further in dissecting one-dimensional NMR spectra by looking at the concept of multiplicity. Multiplicity is the observation that some signals in an NMR spectrum, rather than appearing as these singlets, like I'm circling here, a single peak, instead are split into these subpeaks, such as this triplet that I'm circling here in our sketch spectrum, or a doublet here, or some more complex splitting pattern, such as this splitting here that we could call perhaps a multiplet. So we are going to, in this video, explore why some signals appear as multiplets, as multiple signals here, whereas others appear as these so-called singlets, and how we can apply that information to deduce features of the structures of our organic molecules. We are going to focus this discussion primarily on proton multiplicity. We will get into, in a moment, why carbons don't typically, why we don't typically observe carbon-carbon multiplicity. And we'll go through some of the details of how you can use this to help on our journey of solving chemical structures. So the next question that we will ask is, why do we observe multiplets in NMR spectra? In other words, why don't we just see the signals appearing as single peaks all the way through the NMR spectrum? Well, the reason is that when we think about why NMR, why this nuclear magnetic resonance phenomenon is occurring, when we talked about chemical shift, we mentioned that the protons had a resonance frequency when they were subject to an external magnetic field. And the specific frequency, the resonance frequency, was dependent upon the exact chemical environment of that particular proton. And we talked about the chemical shift being dependent upon whether there were electron donating or electron withdrawing groups nearby as a key influencer of the environment that an individual proton was in, and hence a key determinant of the extent to which that proton was shielded or deshielded from a magnetic field, ultimately impacting its nuclear magnetic resonance frequency. Now, here's the thing. If there are other protons nearby, what is going to happen is that those nearby protons will have themselves a small associated magnetic field that will impact, to a small extent, the absorption frequencies of the proton that we are observing. And these small magnetic fields created by nearby protons will impact the proton that we're measuring in a very predictable way to provide this multiplicity pattern. And this multiplicity pattern will give us predictable clues about the structure of the molecule that we are looking at. So to put something down in writing about this question of why do multiplets occur in NMR spectra, multiplets are going to occur in NMR spectra because two protons are close enough together that their magnetic fields influence each other, and we would say that those protons are magnetically coupled. Now, when we say that two protons are close enough together that their magnetic fields influence one another, and hence they are so-called magnetically coupled, to give a very distinct multiplicity pattern or a very distinct splitting pattern of the signals. How do we define close enough together? What do we mean here when we say that two protons are close enough together? That seems a little bit vague. So let's clarify that. When we say that two protons are close enough together, what we are typically referring to is that the two protons are vicinal to one another. Vicinal means that the proton is on an adjacent carbon atom. So let's draw out an example of what we mean here of the two protons being vicinal. Vicinal is typically what we think of as the protons being close enough together. There are some special scenarios where the protons can be a bit further away than vicinal, but vicinal is our typical case scenario. So let's say we have a proton in red here, bonded to our first carbon atom. I'm just going to fill in generic R groups here onto that carbon to fill its octet. And then we have our second carbon atom, or carbon next door here, that is bonded to a hydrogen atom in blue. And I'm also on that carbon going to plug in some generic R groups as well. And so let's say that we are measuring the NMR signal for the carbon shown in red, for the hydrogen shown in red, the hydrogen that is on the left here. So this is the particular hydrogen that we are measuring the chemical shift for. And so when we're measuring the chemical shift of this particular hydrogen, it will show up somewhere along the x-axis between 0 and 10 ppm. And that position along the x-axis will be primarily determined by what electron donating or electron withdrawing groups are nearby, because that is going to result in this proton being shielded or deshielded, like we learned in the last video about chemical shift. What is then going to influence the multiplicity pattern or the splitting pattern of this particular proton is the more subtle effects that result from the magnetic field of this blue proton that's on the adjacent carbon impacting the exact magnetic field that this particular red proton experiences. So we are measuring the NMR chemical shift for the red proton, but the pattern that that creates is going to be impacted by this vicinal hydrogen, the hydrogen on the adjacent carbon that is shown in blue. So then thinking about the multiplicity pattern that would be observed for the chemical shift of the red proton, what's going to happen is that when we think about the blue proton that the red one is coupled with, that the red one is observing this spin-spin splitting with, remember that the blue proton would have two spin states. And we can represent one of those as being up, and we can represent one as being downward. One of those is going to reinforce the magnetic field that the red proton is experiencing. The other arrow, the other spin, is going to oppose that. And so as a result, we have two different magnetic fields that this single proton is experiencing, coupling with the blue proton. One of those corresponding to one of the spin states of the blue proton, the other corresponding to the other. And so as a result, this red proton is split into a doublet because it's experiencing the two different possible spin states of the blue protons. And so therefore the red proton would show up as a doublet rather than showing up as a single unsplit signal. Instead, what it's going to show up as is two closely spaced signals there. And those two closely spaced signals would have the same intensity, meaning that each of those two peaks are approximately the same height there, because this proton is equally prone to feeling or being subjected to each of the two spin states of the proton on the adjacent carbon atom, giving these two peaks, the two spin states. And so, continuing onward, we can look at the situation if, rather than just having one vicinal proton, what if we had two or more vicinal protons? How can we look at the spins of those vicinal protons impacting the one that we are measuring? So let's go ahead and continue this. And to carry on from the theme that we were just looking at, I'm going to draw a similar structure here on your right, a similar mock structure, where we are going to be looking at the chemical shift and multiplicity of the proton that I've highlighted in red here. And it is vicinal now, not to just one proton in blue, but to 2 protons in blue. And so if we have our proton in red, that is the one we are measuring the NMR chemical shift, and we're looking at the multiplicity of, and we want to think about what its multiplicity would be. So its overall chemical shift is going to be determined by the environment that it's in. In other words, how electron donating and withdrawing are these R groups that are surrounding it and things like that. And then the multiplicity is determined by how many vicinal hydrogens are there. So in this case, we have 2 vicinal hydrogens. And so if there's 2 vicinal hydrogens, and we are going to assume that these are 2 equivalent vicinal hydrogens, meaning that these 2 hydrogens are in the exact same chemical environment. They are going to give the exact same chemical shift, in other words, for these 2 hydrogens there. So if we have 2 equivalent vicinal hydrogens, we can think about what the combinations are of their spin states. So if we have 2 vicinal hydrogens, each of those have their own set of spin states. Each of those, in other words, when put into the magnetic field, can spin what we'll show here as our arrows as either upward or downward. And so when those 2 are both engaged in this phenomenon of magnetic resonance, we have to look at the possible combinations. So the combinations of those 2 hydrogen spin states. So the 2 hydrogens could both have positive spin states simultaneously, meaning 2 arrows up. They could both have, instead of both being oriented up, they could also both be oriented downward. And then there are 2 different ways that we could have the arrows opposing. One is that the one on the left is up, the one on the right is down, and vice versa, down versus up. So we have 4 possible scenarios here, using all the combinations of up and down arrows to represent the spins that these 2 hydrogens, vicinal to the one that we are measuring in red, can be found in. And these different spins are going to impact the exact chemical environment and determine the multiplicity of this proton that we have shown in red here. And so what will turn out to be the case is that these 2 in the middle, up, down, and down, up, appear as a single signal or a single peak when we're thinking about the multiplicity. Then the 2 that are up are unique, and the 2 that are down are unique. And so what happens here, when we think about these 4 possibilities being equally probable, we end up with a signal that we would refer to as a triplet. And in the triplet, what is going to happen is that the peak intensity is at a ratio of 1 to 2 to 1. So the peak on the left here, 1 to 2 to 1, meaning that peak in the middle is twice as intense as the 2 peaks that are flanking it. And the reason is that when we look at the breakdown of the different combinations of up and down spins, the up and down arrows here, we see that the 2 upward arrows give this signal on the far left, the 2 down give the signal on the far right, and then the one in the middle that appears as a single peak is twice the intensity of the others, because of the fact that it is actually a combination of these 2, up and down and up, appearing as a single peak. And so what this phenomenon gives rise to, if we continued drawing this out as all the different combinations of up and down, depending on how many equivalent vicinal hydrogens there are, what we will see is that we can use Pascal's triangle to give us the approximate relative areas of these multiplets, depending upon how many vicinal hydrogens there are. So the relative areas of these peaks of these multiplicity patterns, the relative areas of the multiplicity patterns is going to follow so-called Pascal's triangle. And the reason it follows Pascal's triangle is because Pascal's triangle is going to represent when we have two different scenarios for each and every proton, meaning that they could be up or down in terms of their arrow orientation here, representing their spin states. As we increase the number of vicinal hydrogens, we're going to increase the number of possible arrows and the number of possible arrows that are redundant and not redundant. And so what happens here is that we have a series of established patterns where if we have a doublet, then the ratio of the areas is going to be 1:1 for the two peaks of that doublet. If it's a triplet, like we illustrated up top, the ratio is 1:2:1. If we have a quartet, using Pascal's triangle to predict what's going on, it'd be 1:3 to 3:1 if we drew out all the combinations of up and down arrows that would result from having a quartet. And so we can use these relative areas in order to establish what the multiplicity is of a particular signal by looking for these specific area ratios. And generally this is eyeballed as asking yourself, when you look at a particular peak in an NMR spectrum, does it look like the signals have a 1:2:1 ratio? If so, it's probably a triplet. Or when we look at the peak, does it look like it's more like a 1:3 to 3:1 ratio? Maybe even making that a little bit taller there to represent a quartet. So if we are trying to use this information to solve the chemical structures of organic molecules, what are some things that we can keep in mind, or some general pointers and rules? So our analysis of the various coupling of spin states, as we were just seeing and illustrated with the arrows, can be extended to more complex systems by using the n+1 rule. The n+1 rule says that if a peak, an NMR signal, is split by n, the number of equivalent protons, and usually this is the number of vicinal protons, it will be split into n+1 peaks. And this is split into n+1 peaks because of the fact that when we sum up all of the combinations of up and down arrows, what we are going to see is that the sum of those will be equal to the number of equivalent vicinal hydrogens plus 1. And they will split into that very distinct pattern predicted by the Pascal's triangle, where we can look at the ratios of the different signals within those peaks. We can look at the specific splitting pattern, the ratios of the peaks within that splitting pattern, in order to deduce the number of vicinal hydrogens, because the number of vicinal hydrogens that are equivalent is going to be predicted by this n+1 rule. So if we see that a signal shows up, for example, as a quartet with that 1:3 to 3:1 ratio, we can predict that the proton we are measuring the signal for has to have 3 vicinal hydrogens. So if we were measuring, for example, the hydrogen in red is the one we're measuring the chemical shift for, and we notice that is observed as a quartet, we can conclude that on this vicinal hydrogen, this vicinal carbon, that the hydrogens there have to be a grand total of 3. Because in this case, if we're measuring our proton there in red, our number of vicinal hydrogens equals 3. And so n plus 1 is going to then be equal to 3 plus 1, which equals 4, meaning that the signal is a quartet with that 1 to 3 to 3 to 1 ratio representing the distinct combinations of up and down spin states that we could represent for these 3 protons that the one in red is coupled to. And keep in mind with this that the rule relies upon the protons being equivalent. Equivalent means that the protons are in the exact same chemical environment. It means that the protons have to be totally interchangeable with one another, meaning that generally they are freely rotatable. If you switch one with the other, you would have the exact same structure rather than creating something that is different in any way, shape, or form. And so they have to be in exactly the same chemical environment because otherwise they aren't going to have the same effect on the vicinal hydrogen, and hence they would not give this clear, distinct splitting pattern. Instead, if they're non-equivalent to one another, they're going to give a more complex pattern. And so that's what we're going to look at in the next video, is what happens if we have vicinal hydrogens that are not all exactly in the same chemical environment, but they are in a variety of different environments. What happens then, and what adaptations do we need to make to this n plus 1 rule?